All right, so we're doing section 6.5. Part 2, we're going to do powers, talk about powers and roots. Of complex numbers. So this continues on from what we talked about yesterday when we were talking about complex numbers in trig form. So let's say, just as a reminder, yesterday for multiplication, we said if z1 was r1 cosine theta 1 plus I sine theta 1, and z2 was r2 cosine theta 2 plus I sine theta 2, that when we multiply these two, z1 times z2, we got this really nice way of multiplying these complex numbers here. It was r1 times r2, multiply the moduli, and add the angles. Made multiplication very convenient. Now let's think about what we would do if we were going to find z1 to the nth power. So we're going to remember that finding multiplying something, we're finding a power of something, is we're multiplying it repeatedly. So if we're multiplying z1 repeatedly times itself n times, we would get out in front, we would get z1 times z1 times z1, or sorry, r1 times r1 times r1 times r1 n times. So how would we write that? r1 to the n. So we're multiplying it by itself n times, so that's going to be r1 to the n. And in here, we're adding our angles. So we're doing theta 1 plus theta 1 plus theta 1 plus theta 1, however many times. How do we write that? N times theta 1. We're adding it together, so it's adding, repeated addition is multiplication. So we can write that as cosine of n theta 1 plus I times the sine of n theta 1. So there's how we're going to find powers of complex numbers. So think just for a second. Here we're just finding the power of a real number, and here we're just multiplying an angle times a number. Think about how difficult it would be, even for a relatively easy complex number like 2 plus 3i. Say we want to do 2 plus 3i to the 7th power. Imagine how much work that would involve. All those parentheses and all that distributing and all the combining like terms and I squareds and all of that, all of those steps that would be involved in finding the 7th power of this. If we convert this to trig form, all we have to do is take the 7th power of the modulus and multiply the angle by 7. Write it out in trig form, use our calculator, convert it back to standard form. So much, much, much easier. So let's take a look at an example of finding the power of a complex number. Just follows on from what we did yesterday. So we want to find negative 2 square root of 3 minus 2i to the 5th power. So the first thing we're going to do is convert this to trig form. So we're going to find our r. R is going to be the square root of negative 2 square root of 3 squared plus negative 2 squared. And this gives us the square root of negative 2 square root of 3 gives us, when we square that, we get 4 times 3 plus 4. So we get the square root of 16, which is 4. And then we're going to find our theta. Theta is the inverse tangent of negative 2 over negative 2 square root of 3, which gives us the inverse tangent of 1 over the square root of 3. So we want, let's see, in what quadrant are we in here? Third quadrant. So we want a third quadrant angle whose tangent is 1 over the square root of 3. Remember what that angle is? And we're in the third quadrant. So we want, so our inverse tangent, so we need our square root of 3. We need the square root of 3 in the denominator, sine divided by cosine. So, what's that? 240, or in radians? So we're in the third quadrant. So, is it, so we need our, so tangent is sine over cosine. So we need the square root of 3 in the denominator. So the cosine, the x-coordinate is the longer side. So is it going to be a fraction of 3 or fraction of 6? Fraction of 6. And we need to be in the third quadrant. So it is 7 pi over 6. Whew. Unit circle was a while ago, huh? So our theta is 7 pi over 6. So our fifth power here, so negative 2 square root of 3 minus 2i to the fifth is going to be r to the fifth, so 4 to the fifth times the cosine of 5 times 7 pi over 6, so 35 pi over 6, plus I times the sine of 35 pi over 6. Four to the fifth is 1024. And here's another one, unicircle one. Cosine 35 pi over 6. 35 pi over 6 is coterminal with what angle? 11 pi over 6. Because 36 pi over 6 is coterminal with 2 pi. And we're a negative pi over 6 from that. So we're looking at the cosine of 11 pi over 6, which is square root of 3 over 2. And the sine of 11 pi over 6? Negative 1/2 I. So when we calculate this out, we get 512 square root of 3 minus 512i. So if we can remember our unit circle, or I guess we could use our calculator, this is much easier than trying to multiply this parentheses that times itself 5 times. So this would be the fifth power of negative 2 square root of 3 minus 2i in trig form and in a plus bi form. Questions there? Just like we talked about yesterday, way easier to find powers of complex numbers by converting them in trig form first. And our numbers don't always turn out to be nice unit circle angles where we can find the sines and cosines easily. And then we use our calculator. Calculate the sine, the cosine, calculate our powers with our calculator and multiply it out that way. And we call this this theorem for finding the powers of complex numbers in trig form. This is DeMoivre's theorem. So you'll hear it's if you hear DeMoivre's theorem, you'll know what it's like. So Mr. DeMoivre was pretty clever coming up with that theorem. All right, so the next thing we want to do is go the opposite direction. Rather than finding a power of a complex number, we want to find a root of a complex number. All right, so let's think about what's going to happen if we have some number and we want the root of a complex number. So let's say that our complex number, I'm going to call it u, and we're going to say that u is a times the cosine of beta plus I sine beta. And u, we're going to say, to come up with our idea here, u is the nth root of this other complex number z equals r cosine theta plus I sine theta. Well, if u is the nth root, that tells me that a to the n times cosine of n beta plus I sine n beta equals z. So if we have the nth root, if we raise the nth root to the nth power, that the root and the power undo each other, and we get back to our original number. If we look at the parts here, if we compare the parts, that tells me that a to the n has to be r, or a equals the nth root of r, and if we look at our angles, then beta has to be theta over n. And we have to be a little bit careful here because we could get it could be theta or any of its coterminal angles. So any of the coterminal angles are going to give us the same complex number. So the way we write that, just like we did when we talked about the unit circle, I'm going to say theta plus 2 pi k over n. So in order for this number to be an nth root, these things have to be true. And this 2 pi k lets us get all of the coterminal angles of theta. And the way it works here is because we're taking, I want to make this, my end is not coming out really well here. There, that looks better. The way this works out is k is going to be 0, 1, 2, up to n minus 1. If k equals n, we've gone all the way around and we get back to where we started. So k is just going to go 0, 1, 2 to 1 less than n. And that gets, when we get back, when k equals n, we've gone all the way around our unit circle, and we get back to where we started. So this gives us a way to find the nth root of a complex number. So we're going to say the nth root of z equals r cosine theta plus I sine theta equals, put it down here, the nth root of z equals the nth root of r times the cosine. We want our angle plus our plus any coterminal angle, theta plus 2 pi k divided by n plus I times the sine of theta plus 2 pi k over n, and k goes from 0 to n minus 1. Now this formula looks confusing. There's a lot of k, the k, the n, the divide, the 2 pi n. So again, going back to what we said up here, all we're doing is saying that in order for this to be an nth root, when I raise it to the nth power, it has to equal our original complex number. And so beta, this angle, has to equal theta over n, or it could be theta or any of its coterminal angles. So we have to make sure we get all the coterminal angles in there. And we divide that by n. That's all we're saying. So we're going to do a couple of examples of these. And we'll also talk about what this means geometrically. So what does it mean in the complex plane? All of this stuff about theta plus 2 pi k over n. And another way, so the other thing that we can think about here is think about when we talked in chapter 2 about finding the roots of a polynomial. If we had a 5th degree polynomial, we knew we were going to get 5 roots. So if we're taking the 5th root of any number, we get 5 possible roots, because we could think of that number, the 5th root of a number, is like saying x to the 5th equals, say, 7. So we're going to take the 5th root of 7. We should get 5 5th roots because this polynomial has 5 solutions. Well, that's what this, letting k go from 0 to n minus 1 gives us those 5 5th roots. All right, so let's look at a couple of examples. So don't get worried about the n's and the k's and all that thing. It's really not that complicated. All right. So questions before we go on. And this just comes from thinking about the nth power in reverse. All right. So let's find we want to find the fourth roots of 16. We have a fourth, we could think of this as a 4th degree polynomial. X to the 4th equals 16. So it should have 4 solutions. So the first thing we're going to do is write 16 in complex form, in trig form. So 16. What's our, for real number 16, what is our r? What is our modulus? Here's a little sketch. There's our number 16. How far away is that from the origin? 16. So it's going to be 16. What's our angle here on the x-axis? 0. So 16 cosine 0 plus I, I'm going to say 0 degrees, 0 degrees. 0 degrees or 0 radians. Let's do radians. So erase it. So the fourth root of 16, or the fourth roots of 16, is going to be the real fourth root of 16 that we get when I plug in our calculator, times the cosine of 0 plus 2 pi k over 4. Thank you. And then we need our imaginary part here. So the I plus I sine 0 plus 2 pi k. So we get all of our coterminal angles over 4. And we're going to let k equal 0, 1, 2, 3. N is 4 here, so we go 0, 1, 2, 3. So we calculate this out 4 times. We'll plug in k equals 0, k equals 1, k equals 2, k equals 8. And we'll get one of our roots from each of those. So in our calculator, what's the fourth root of 16? What is it? 2. So we get 2. So I'm going to say k equals, we'll do our calculation for k equals 0. 2 times the cosine. We're going to multiply 2 pi times k, so I get 0 plus 0 over 4 is 0. Cosine of 0 plus I sine 0. What's the cosine of 0? 1. Sine of 0? 0. So this just equals 2. So there's our real fourth root of 16. Now we're going to plug in k equals 1. So we get 2 times the cosine. I'm plugging in 1 for 2 pi here, 1 for k here. So I get 2 pi over 4, which is pi over 2, plus I sine pi over 2. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So we get 2i. And if you multiply 2i by itself 4 times, you'll get 16. Now let's let k equal 2. So we get 2 times the cosine of 4 pi over 4 plus I sine pi. Cosine of pi is negative 1, sine of pi is 0, so I get negative 2. So negative 2 is a fourth root of 16. And I get, for k equals 3, I get 2 times the cosine of, multiply 2 pi times 3, so I get 6 pi over 4. So that's going to be 3 pi over 2 plus I sine 3 pi over 2. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1. So I get negative 2i. So those are my fourth roots of 16. My 4 fourth roots of 16. Notice that my complex roots are complex conjugates. So we said when we had a polynomial, the complex roots showed up in conjugate pairs. Our geometric interpretation of this, what this tells us in the complex plane. If I plot these in the complex plane, draw straight. Here's 2. Here's 2i. Negative 2. Negative 2i. our solutions end up on a circle. In the complex plane. The radius is R2, so my radius is 2, and each root is separated by 2 pi over 4, or pi over 2 units. So our roots end up on a circle with radius r, whatever our r is, and the angle, they're equally distributed around the circle at in intervals of 2 pi over n, whatever the root is that we're taking. So if here we have 2 pi over 4 or pi over 2, so it's every pi over 2 units, I get a new root. So what I could do is find my original angle. My original angle is 0, and I find a new root every pi over 2 units at radius r, and that's going to be my point. So that's what this 2 pi k over 4 is telling us, that our roots are symmetrically distributed around the circle at pi over 2 units in this case, 2 pi over 4. And that's always going to be the case with these complex roots. They're always going to be on a circle with radius r, and they're always going to be symmetrically distributed, and the angle between each root is going to be 2 pi over n, whatever our root that we're taking. Questions there? Okay, let's look at another example. This one a little different, because it turns out this one was nice and symmetrical because our angle turned out to be 0. We've got all of our roots ended up on our coordinate axes. All right, so let's find the third roots. Three third roots of 4 square root 3 minus 4i. So the first thing we're going to do is write this in trig form. So my r is going to be the square root of 4 square root 3 squared plus negative 4 squared. So I get the square root of 16 times 3 plus 16. 16 times 3 plus 16 is 64, so we take the square root of 64 and we get 8. So r equals 8. Theta is the inverse tangent of negative 4 over 4 square root 3. So we're looking for the inverse tangent of negative 1 over square root 3. And what quadrant are we in? Which one? Fourth. So what's our angle in the fourth quadrant that gives us a tangent of negative 1 over square root of 3? 330, or 11 pi over 6. So theta is, we can say 330 degrees, or 11 pi over 6. So the third roots of 4 square root 3 plus 4i is going to be the third root of 8, the real third root of 8, times, let's write this in degrees rather than radians, cosine of 330 degrees, and when we're in degrees rather than 2 pi, we're going to say 360 plus 360 degrees times k over 3 plus I times the sine of 330 degrees plus 360 times k over 3. And here k is going to be 0, 1, and 2. So because we're using degrees, we write it as 360. So we're going to do the same thing, k equals 0, and so what we're going to do for this one is, what is 360 divided by 3? Divided by 3? 120. So 120 degrees. So each time we find a root, we're just going to add another 120 degrees to our angle. So we'll start at whatever our original angle is. For k equals 1, we'll add 120 degrees, and for k equals 2, we'll add another 120. So we start at our original angle, whatever our original angle is, and add 120 each time. So the third root of 8. So for k equals 0, the third root of 8 is 2 times the cosine of 330 divided by 3, and k equals 0, is 110 plus I sine 110. So this doesn't give us nice unit circle angles, this particular problem. So our original angle is 330. So our first, when I calculate this out, I get this is approximately negative 0.684 plus 1.8794 I. So what we could do is we figure out where this is on the graph, and then we would add 120 degrees each time. So yes, you could do it that way. So this is our first third root. For k equals 1, we're going to do 2 times, and we're just adding. We're adding 120 degrees to our original angle. So our roots are separated by 2 pi over n, or 360 over n, symmetrically around the circle. So now we can find 2 times the cosine of 110 plus 120. So 230 plus I times the sine of 230. And when I calculate this out, I get that this is about negative 1.2856 minus 1.532 I when I calculate this in my calculator. And for k equals 2, I'm just going to add another 120 degrees here. So I get 2 times the cosine of 230 plus 120 is 350 plus I sine 350. And when I calculate that, I get that this is about 1.9 696 minus 0.3473 I. So I find my original angle. The roots are symmetric around the circle at every 120 degrees, so I just added 120 degrees each time to my new angle, and I get my new point. So if I plot this, and then if I added another 120 degrees to 350, I would get back to where I started. So if I plot this in the complex plane, my points would be, my first one would be up, it's not exact, but somewhere about here. My second one would be down here. And my third one comes out to be here. So I'm around this circle. And I know I didn't do my drawing perfectly, but it's close, fairly close. The radius here is 2. And these angles are 120 degrees. So those would be my points around the unit circle. Symmetrically arranged, or not the unit circle, around this circle with radius 2. Questions there? Okay. This finding powers and roots of our complex numbers in trig form, a very, very powerful tool. And you go further, I remember one class I remember really distinctly working with this idea a lot was optics. When I took an optics class when I was a physics major. We did talked about the light, propagation of light. I said there's a relationship between complex numbers and exponential functions. We represented all the light waves with exponential functions with complex numbers, and we did this kind of thing, this kind of calculation for talking about light going through lenses and that kind of thing. I remember doing this for the entire year in optics class, doing these kinds of things, working with complex numbers in trig form. So I just doing these examples brought back a really strong memory of that class. So very useful, very powerful tool. And if you go further in science, engineering, or mathematics, this will show up in places that it might surprise you where it shows up. All right. Homework. And then I know just a lot of individual numbers. I picked out individual problems. It was too hard to pick out something through something even or whatever. All right, there you go.